All right, one more example where we deal with these polynomials in their unfactored form. And we first get them into their factored form by listing the possible rational roots and then doing some polynomial long division. And then once we have them in their factored form, we come up with the graphs. That's kind of the outline for the previous problems and the same that we'll be doing here. So where you want to start on a problem like this, what I'll ask you to do if this is a test, is to list all the possible rational roots of this polynomial. And as we learned in a previous video, possible rational roots always come of the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. So we look for the factors of 10, which are 1, 2, 5, and 10. And then we look for the factors of 1 for the implied 1 in front of this x to the fourth power, which is just 1. And then we take any of these four numbers and divide them by this one number. So that leaves us with possible rational roots of plus or minus 1 divided by 1, 2 divided by 1, 5 divided by 1, and 10 divided by 1. There are only 8 possible rational roots for this fourth degree polynomial. And you're like, all right, these are the possibilities, but which ones are actually roots? Well, if we give this thing a name, maybe I'll use g of x this time instead of y, we can figure out if something's an actual root by evaluating g of that number. In other words, put these numbers into the machine and see if 0 comes out. So maybe we'll start by putting 1 into the machine because arithmetic with 1 is fairly easy. G of 1 would be 1 to the fourth power minus 3 times 1 cubed minus 3 times 1 squared plus 15 times 1 minus 10. So let's see, 1 minus 3 plus 15 minus 10. Does that equal 0? I think it does, right? We have negative 16 and positive 16. So this ends up being equal to 0. So 1 is a root of this polynomial. And that's important because once you find one root, you can significantly simplify things using polynomial long division because each root has a factor that corresponds with it. So if 1 is a root, then x minus 1 is a factor. So our original polynomial, which was x to the fourth minus 3x cubed minus 3x squared plus 15x minus 10, can be divided by this factor x minus 1, and when we do this polynomial long division, we should expect there to be 0 remainder. The idea with polynomial long division is to get rid of columns one at a time, working left to right. So to get rid of this x to the fourth, I'll toss an x cubed up here. X cubed times x minus 1 is x to the fourth minus 1x cubed, and then I subtract. Before I do this subtraction, a quick comment that I want to make is in this polynomial we have a fourth degree term, a third degree term, a second degree term, a first degree term, and a 0 degree term. But if we were ever missing a term, it makes life a lot easier if you space things out so that you have room for each of the different terms. So what I'm saying is if my polynomial was x to the fourth minus 3x cubed plus 15x minus 10, if this minus 3x squared weren't here, it would make your life easier to put in plus 0x squared if this term didn't exist, so that later on when you do all your work, you have columns to subtract in. That's not the case in this example, so I'll get rid of it, but just a helpful little hint in case you ever encounter that situation. Anyways, my next step is to subtract. This first column goes away. This column, you got to be really careful. A lot of people make mistakes in this stage. It's negative 3 minus negative 1, and when you're subtracting a negative, you're adding. So think about it like it's negative 3 plus 1. So when I take negative 3x cubed and subtract negative 1x cubed, I get negative 2x cubed, not maybe negative 4x cubed or something. And then I bring down my next term, the negative 3x squared. And the good news is if you can get this far, you're good because all you're going to do is repeat that process several more times. Instead of trying to get rid of this x to the fourth, now my goal is to get rid of this negative 2x cubed. So instead of putting an x cubed up top, I'll put a negative 2x squared up top. Why negative 2x squared? Because when I take that and multiply it by x minus 1, I get negative 2x cubed plus 2x squared. And when I subtract that product from the line above, my leftmost column will go away. Again, I'll have to be careful in the subtraction over here. Negative 3 minus 2 more leaves me with negative 5x squared. And then I bring down this 15x and repeat again. Instead of trying to get rid of the negative 2x cubed, it's now negative 5x squared that I'm trying to get rid of. So to get rid of that, I'll toss a negative 5x up here because negative 5x times x minus 1 gives me the negative 5x squared that I was looking for, and it also gives me a 5x. When I subtract, the x squared column goes away, and 15x minus 5x is just 10x. I bring down this negative 10. I have one more step. I want to get rid of the 10x. Do so by putting a 10 up here because 10 times x minus 1 is 10x minus 10. And when I subtract, we see that not only did I get rid of the leftmost column that I needed to, but I also get rid of the right column. I get a remainder of 0, which I was expecting because x minus 1 is a factor of this polynomial. It must divide evenly into this polynomial. What we've done is we've changed this fourth degree polynomial in blue into a product of a linear term x minus 1 and a third degree polynomial x cubed minus 2x squared minus 5x plus 10. The good news is it's not the completely unfactored form that it used to be. The bad news is we still have a third degree polynomial, so we still have some work to do. In fact, the work that we still have to do is kind of the exact same thing. We want to continue to factor this third degree polynomial, so pretend the original problem was x cubed minus 2x squared minus 5x plus 10. Let's see if we can factor this thing, and then we can replace these parentheses with the factorization that we come up with. How would you factor this thing? Well, first you'd list the possible rational roots by taking factors of the constant term, which again is 10, so its factors are 1, 2, 5, and 10, and dividing them by factors of the leading coefficient, which again is just 1, so the only factor is 1. We get that possible rational roots are plus or minus 1, 2, 5, and 10. In this case, they're the exact same possibilities that we had for our fourth degree polynomial, but that's just because the constant term and the leading coefficient are the same as they used to be. They won't always be, so it's worth relisting your possible rational roots. Now you start checking them until you find one that works. You might be able to just look at this and tell that 1 isn't going to work. I'm not going to be able to get enough negative to cancel out this positive 10. So maybe 2 is a good place to start. Maybe I should give this polynomial a different name, I don't know, like h of x or something. And then let's see what comes out of this polynomial when I put 2 into it. Well, let's see, I'd have 2 cubed minus 2 times 2 squared minus 5 times 2 plus 10. That's looking pretty promising. 2 cubed is 8. Minus 2 times 4 is minus 8. Negative 5 times 2 is negative 10. But then I also have this positive 10. I end up with 0 here. That's good news. That means that 2 is a root of this polynomial that I'm calling h of x. So that means x minus 2 must be a factor. If x minus 2 is a factor, I can do polynomial long division with x minus 2 and this polynomial h of x, x cubed minus 2x squared minus 5x plus 10, to rewrite this third degree polynomial as a product of a linear term and a second degree polynomial. To figure out what that second degree polynomial is, I just have to go through my polynomial long division algorithm. So I get rid of this x cubed by tossing an x squared up top. X squared times x minus 2 gives me x cubed minus 2x squared. And I subtract. When I subtract, I see that the left column goes away like it's supposed to, but kind of an interesting thing happens here. When I take negative 2x squared and subtract negative 2x squared, the x squared column goes away as well. So I kind of get 0x squared right here. You can write 0x squared if you want and continue through the algorithm, but I think it's easiest when you get rid of 2 columns, just bring down 2 in the next step. Negative 5x plus 10. And then try to get rid of this negative 5x plus 10. Let's see, negative 5x plus 10. To get rid of that, I'd need a negative 5 up top. Maybe I'll write it way over here to kind of keep things lined up. Negative 5 times x minus 2 gives me negative 5x plus 10. I subtract, and again, both of the terms go away, so I'm left with the remainder of 0. What does that mean? It means this polynomial h of x can be rewritten as x minus 2 times x squared minus 5. But remember, this polynomial h of x is what we saw in the parentheses here. So my original polynomial, the fourth degree one that I was calling g of x, is x minus 1 times x minus 2 times x squared minus 5. I've got a product of linear and quadratic terms, so I'm done using polynomial long division. In fact, I'm pretty close to getting my final answers. One thing to be a little bit careful of here. In all of our previous examples, we factored so that we had this as a product of linear terms. We factored this further into x minus something times x plus something or something like that. In the past, I've picked numbers so that these will always factor. But in this specific case, it won't factor, at least not over rational numbers. What that means is that we're kind of done at this step. This is as far as we can go or will want to go by factoring. And you're like, but wait a minute, how can I figure out all of the different roots if it's not factored totally? Well, think about the way that we get the roots is we figure out what values of x will make this thing equal to 0. So really we're just solving x minus 1 times x minus 2 times x squared minus 5 equals 0. And because we know how to solve first and second degree equations, once we break this up into 3 different equations, x minus 1 equals 0, x minus 2 equals 0, and x squared minus 5 equals 0, we can just solve these 3 equations. From this first equation, we get the root at x equals 1, which we found above. From this second equation, we get the root at x equals 2, which we found down over here. And from this third equation, if we add 5 to both sides of the equation and then take the square root of both sides of the equation, we get plus or minus the square root of 5 as roots of this polynomial. Note that the square root of 5 is not a rational number, so it didn't show up in our list of possible rational roots. Right? The key word in here is that these possibilities are just the possibilities for the rational ones, the ones that you can write as a fraction. You cannot write the square root of 5 as a fraction, so it doesn't show up in that list. But that's okay, we're still able to locate these roots after we find these other rational roots and use polynomial long division. So to finish the problem at this step, what we do is we'd go all the way back to our original polynomial and recognize that the y-intercept should be at -10, so here it is in my picture, and that there should be x-intercepts at 1, 2, and plus or minus the square root of 5. Well, 1 and 2 are easy to locate. The square root of 5 is a little harder to find, but the square root of 4 is 2. So the square root of 5 is going to be a little bit more than 2. So maybe I'll put it right here in my picture and right here in my picture for the positive and negative values. In case that's unclear, we can actually label those with root 5 and negative root 5 for the purpose of the reader. All these roots have a multiplicity of 1, so it's easy enough to connect the dots. We don't really even need to check the end behavior. We can kind of tell that it's going to end up looking like this. But if we wanted to verify our answer, we can come back up here and be like, because of the leading term having a positive coefficient and an even exponent, it's going to go up in both directions, so it has the end behavior that we depicted. Takeaway for this video is twofold. First of all, if you have a 4th degree polynomial, you might have to go through this long process of listing the possible rational roots and doing polynomial long division twice, but that's okay, it happens sometimes. If you can do it once, you can do it a second time. And also, sometimes when you're factoring these guys, you'll end up with a quadratic factor that you cannot factor into linear terms. You get stuck here. But that's totally fine too, just set it equal to 0 and solve, since you know how to solve 2nd degree equations. Sometimes it's easy like is depicted here. Sometimes you might have to use like the quadratic formula or complete the square. But either way, you can find all the different roots that you need so that you can sketch the approximate graph and be done with the problem.